You're listening to the University of Liverpool Podcast, brought to you by the University of Liverpool online programs. Make a plan to advance your career today. Study a postgraduate degree with a world-class university without leaving your home or full-time job. You don't have to go far to go further.
Welcome to the University of Liverpool Podcast. I'm Neil Morrison. We're going to try something new here on the University of Liverpool Podcast. Now you may say, hold on, this is just the 5th episode, so really everything we do is still pretty new, and this is true. However, up to now, we have only done one topic per episode. So there was just one on the Beatles and Liverpool, just one on nanomedicine for HIV, and so on. But today's episode is just part one of a 2-part series we want to do on big data and the ethics of autonomous machines. Okay, that's a mouthful, so let me try to break it down. Let's think about a self-driving car. Imagine the decisions the computer inside that car needs to make. Driving speed, stopping distance, when to turn and when to go straight. But the decisions we are going to explore over the next 2 episodes go much deeper than these simple mechanical choices. From time to time, it's possible the self-driving car will find itself in a tricky situation, one where there's really no perfect choice. For example,
if you're faced as a human driver with an option where there's no good answer.
Simon Maskell is a professor of autonomous systems at the University of Liverpool.
So you're driving along, you've been obeying the rules of the road perfectly sensibly, and a person on the other side of the road swerves. That in itself has nothing to do with you, but then a cyclist, perhaps you in this case, who was behind the car in front, swerves now in order to get out of the other car in front of you. So now you, the autonomous car, have a choice of running over the cyclist or steering away from the cyclist into the hedge that runs along the side of a school. So do you run over the person that you know is in front of you because of a fear of people that might be on the other side of the hedge? Or do you just avoid the Canadian interviewer and run through the hedge because actually the chances that it's school kicking out time is so low that it doesn't seem likely that you're going to just have mown down a mother and her 2 small children. And that, when you've got no information about what's on the other side of the hedge, you don't know what the age is of the human being in front of you. You don't know all these things. You have to make a judgment call. And you can run all the numbers, but ultimately it boils down to a set of priorities or choices and things which are very, very hard to see that a computer would ever be able to get right, mostly because people won't agree on what the right answer is, and they certainly won't agree what the one right answer is that transcends each of multiple scenarios.
So in the situation Simon lays out here, a car trying to avoid a Canadian cyclist, the driver, in this case a computer inside a self-driving car, is forced to make what Simon calls a judgment call. Now, in this scenario, Simon said the cyclist is Canadian, and so that, of course, skew things a bit, since, of course, the right decision is to avoid hitting the Canadian cyclist at all costs. But it's a thought experiment, so let's play along. In this case, the computer needs to make a judgment call. Now, Louise Dennis argues that this is a special kind of judgment call, Louise Dennis is a researcher at the Autonomy and Verification Laboratory at the University of Liverpool. She says these kinds of judgments are inherently ethical decisions. Again, imagine the car that must choose between the cyclist or going through the hedge in front of a school.
So that sort of ethical question is quite likely to arise in some form in cars. And then the question is, are we just interested in the greatest number of people? Do we care whether they're children or adults? Do we care if they have a criminal record? Personally, I think we shouldn't, but I can see it being very attractive to people to say, well, no, I want some value judgments made about these lives, which I might potentially be going to take. And of course, do we care whether it's the life of someone on the road or someone in the car? Is it more important to protect the driver and their passengers than it is to protect bystanders?
In this two-part series on big data and the ethics of autonomous machines, we're going to explore these ethical scenarios and what they mean for how we think about and design autonomous machines. We will hear more from Louise Dennis in our next episode, but this week we are speaking with Simon Maskell. Now, one of Simon Maskell's areas of research is in big data and autonomous systems, and one project he was recently involved with was the hunt for MH370.
Delivery manager 370, good morning.
MH370 was the Malaysian Airlines plane that went missing less than 1 hour after takeoff from Kuala Lumpur on March 8, 2014.
Malaysian 370 standby and Malaysian 6 is cleared to Frankfurt via Agosa Alpha departure 6006.
So there was an aeroplane called MH370. It took off from an airport in Malaysia. It was, I think, a scheduled flight going to Beijing, which is something like 6 hours away in an aeroplane. And it took off. It was observed by some radars, as it would normally be. Did a few slightly odd things, but nothing particularly unusual in some respects. And then it disappeared off the edge of the radar trace. And at one level, nothing ever has been seen of it since. The fact that it had relatively recently taken off, and the fact that you can travel quite a long way if you've got 6 hours worth of fuel, or probably about 8 hours worth of fuel actually, means that the set of places you can get to if you're an aeroplane that's pointing in any direction that's possible and you start somewhere near Malaysia is immense. It's kind of a massive chunk of the earth. So if that's all we had to go on, we'd have to search most of the Indian Ocean, quite a large chunk of the Himalayas, all kinds of weird and wonderful places that would just be so huge a task to find an aeroplane that it just wouldn't happen because you wouldn't know where to start looking. So what some extremely clever people spotted is that there were messages exchanged with the aircraft after it disappeared from the radar's field of view. So the aeroplane has disappeared and yet it's still talking. So what they did is they looked carefully at the information that was inherent in these conversations between what turns out to be essentially a satellite and the aeroplane. So it's just the aircraft saying, yep, everything's fine, and happens once an hour. It's perfectly routine, and up to the point where MH370 was in the news, I think people had the hunch that it could be useful for figuring out where an aircraft was, but nobody actually, for example, used it. So,
and I just want to clarify something. These are automatic exchanges. These are done by the airplane itself and the satellite and the ground stations. It's not something the pilots are initiating, right?
So I'd be very interested to know, but I suspect that the people on the aeroplane, whoever they were, and the whatever their intent, including the pilot and co-pilot and so on, will have had no idea that the aeroplane was talking in this way, as you say, with the ground station via the satellite. It's kind of, I think it's probably a bit of luck that somebody spotted that this aeroplane that had disappeared was still talking. So now, if you've got an aeroplane that's talking, you can say, well, hold on, what's it saying? And there were two kinds of things it was saying. The first basically gives you a circle that the aircraft is on, and that circle is huge. So it has a diameter that I think is roughly the size of Australia or Europe or North America or something like that. So it's a massive circle. So at each of a small number of points, of which you have about 5 or 6, you say, I'm somewhere on this circle at this point in time. And then you have some other measurements that say the size of the circle I'm on is growing or shrinking to this extent. So that gives you a sense as to, is the aircraft moving away from the satellite or is it moving towards the satellite? Doesn't tell you anything about how it's moving tangentially, but it just tells you, am I moving towards the satellite or away from the satellite? It's a bit more complicated than that, but that gives you the intuition. So you've got measurements of position, but extremely vague, and measurements of speed and heading, but extremely vague. But crucially, you have a few of these, and they're relatively far apart. Since they all happen after the measurement, so that the aircraft has migrated out of the field of view of the radar, you can start saying, well, what does that tell us? So the approach taken is then you say, well, let's imagine that the aircraft was traveling due north. Let's assume it was traveling at this speed. Let's assume that the satellite was moving in the way that we know it's moving, because it's not perfectly stationary above a specific point on the Earth's surface. It's a satellite that's wobbling around a bit. But you can work out, well, hold on, doesn't really look like the aircraft could have been moving north, because that would have implied that the circles that we described perhaps were growing, and actually they shrunk and then grew again. So it doesn't look like it's going north. So let's have a go at it going due west. Well, if it went due west, then the circles would have shrunk, but as I say, they shrunk and then they grew again. So it doesn't look like it's going due west. And you can run through lots and lots of different hypotheses and not actually only consider straight lines, but you can look at, well, what speed was it going? What direction was it going? Does it look like it changed direction, and so on? And from doing that, you can figure out which trajectories that it might have taken are those which are consistent with the measurements that this conversation with the satellite measured. And that's what enables you to narrow the search area from something that's just infeasible to tackle because it's a large fraction, I'm guessing, but let's say 1/10 of the Earth's surface, to something that you could feasibly spend an enormous amount of money, time and effort searching and actually have a chance of finding an aeroplane.
Okay, let's pause here for a moment, because though it might not seem like it, this is where the hunt for MH370 is similar to the problem facing the driverless car. Let's start with MH370. At first glance, it looks like this is not a big data problem at all. In fact, it looks to be the exact opposite of big data. The searchers had very little information to work off. They knew how much fuel the plane carried. They knew how far that sort of plane could travel on that amount of fuel. Then they had these little pings, the automatic signals the plane sent out to the satellite every hour or so. And that's about it. Now, that doesn't seem like a big data problem. What it looks like is a big problem caused by the serious lack of data. This seems very different from the big data problem we can imagine a driverless car faces. Imagine you have a Google Maps view of your car on the road. As you zoom in on your car, you see the enormous range of things your car needs to pay attention to. There's the traffic, of course. Then there's the weather, traffic lights, bikers, pedestrians, construction. There's the skateboarder cutting across the road, the dog that is straining to get off its leash. The list goes on. This seems like the quintessential big data problem. There is a lot to process, and the car needs to process it very quickly. So a driverless car is clearly a big data problem, whereas MH370 looks like a small data problem. But hold on. MH370 was just one of thousands of flights cutting across the skies near Malaysia on that day. People have made animations of all the flights taking off and landing across Asia over a 24-hour period. Each flight is represented by a little yellow dot, and the yellow dot starts at one place and floats across the screen to another spot. There are so many yellow dots, the screen is almost entirely yellow. It's like a nature film that zeroes in on one plant just as an explosion of pollen is carried in the wind. Each one of these dots is a plane, and each one of these planes is sending out its own ping to satellites. So there are thousands of pings coming from thousands of flights, and what you are looking for is your ping. The one ping, MH370's unique ping in that swarm of data. So here's how the data problem a driverless car faces is similar to the data problem searchers faced in the hunt for MH370. The challenge is to cut through a thick cloud of data to zero in on the bits of information that are critical to your specific situation. A driverless car needs to be able to not pay attention to the construction on the next street if it doesn't affect the cars immediately around the vehicle. It doesn't need to care about the weather, unless the roads are particularly wet and slippery right now. It needs to filter out the barking dog, as long as it stays on its leash. It does need to look out for that skateboarder who is about to cross the road right now. The challenge big data analysis works through is not just crunching a vast array of numbers to come up with an average. The challenge is to sift through the numbers to find the specs that apply to you and are relevant to your situation right now.
This drive towards personalized analytics means that the data set that's relevant to each individual is actually quite small. So it normally gets hidden in a mass of other small data problems that together constitute what people think of as a big data problem. So what I think makes MH370 an interesting case is that there are hundreds and hundreds of aeroplanes flying around at this very instant, but actually it's only this one aircraft and its one experience at one point in its lifetime that is specifically of interest, and all that other data that you could go out and analyse, and the Australian government did use data from other aircraft to understand how to calibrate the various things they were doing. But all that other analysis is kind of secondary to the fact that there are a very, very small number of data, and those very few data have some information in them, and it's tricky to get that out. And that's really the nub of what I think makes MH370 a really tough but also interesting problem to look at.
Now, when you're using computers to do that analysis, are you using them simply as sort of giant calculators to just crunch through a lot of calculations that you or a human is entirely in control of? Or is it the sort of process where along the way the computer needs to make some decisions about how it's going to view things as well?
So the computer is able to do an awful lot more calculations than a human being, but there would be nothing stopping a vast room full of human beings doing the analysis that has been done with MH370. You just need a few 100,000 people with a few 100,000 hours each to spend on the problem, and that would be fine. So I guess I see it the other way around, which is that, so what you want to do is to have a computer to do the work that the human beings would have been wasting their time to do, such that the human beings can focus on the things that the computer finds difficult. And the computer finds human judgment difficult to handle because it's a computer, it's not a human.
What were some of those key judgments that humans needed to make along the way here?
So in the analysis that was done, there are necessarily assumptions. So broadly speaking, aircraft tend to fly in straight lines, but it's quite likely that the aircraft changed its heading at various points. So then you have a kind of question as to, well, when did it change its heading? How often do aircraft change the heading? And you could make assumptions about how many of such heading changes occur at each of, per hour or some other kind of unit of time. But those are kind of things that you could measure and you could hypothesize about, and the army of computers that are going away running all these tasks that a human being could have done can run through all those things and tell you what the data says is most likely. The much, much harder thing to make any judgment about is what was going on in the head of the person or people in the cockpit, assuming they were present, because there is no, at least at first sight, information that tells you what they were thinking. And there's also no direct information as to whether or not they were conscious. So clearly a conscious pilot and an unconscious pilot are going to interact with the controls of the aircraft in fundamentally different ways. And a conscious pilot who has some malicious intent will almost certainly be thinking differently to the other pilot in another parallel universe who was working in the best interests of the people on the aeroplane.
Right. I mean, one possibility could be that the pilots were trying to evade anybody's ability to track what they're doing.
Exactly. And I think trying to second guess what the people in the cockpit were thinking is really tough, really, really tough. And it has a very significant impact on where you should look. And the reason that's the case is that, broadly speaking, the analysis that's been done provides a fairly accurate position and speed for the aircraft at the point where it ran out of fuel. Now, if you're an aircraft that runs out of fuel at a height above the ocean, and there's nobody in the cockpit doing anything, then the aircraft drops fairly suddenly and hits the surface of the ocean, relatively speaking, close to where it ran out of fuel. If, however, the pilot chooses to try to glide the aircraft down to the surface of the ocean, then the aircraft will move in a very different manner and will end up in a very different place. And the size of the search area, as we've talked about, is large. That's the search area that results from a rapid descent. The search area that results from a slow descent is bigger and would be extremely hard to search with any degree of confidence that your search would have a high chance of finding the aircraft.
Mm-hmm.
So this hypothesis that you have to conjecture about, was it the case that the pilot was consciously trying to glide the aircraft or not, has a very dramatic impact on where you should look. And at first sight, there's no information that tells you what the state of mind of the pilot was at the point where the aircraft ran out of fuel. And maybe there wasn't anybody in the cockpit. Maybe there was somebody with malicious intent in the cockpit. Maybe there was somebody who was unconscious in the cockpit. You just don't know. And that means that there are these fundamental uncertainties that no amount of analyzing the data from the satellite is going to tell you.
And they are, at the end, they're for a searcher or for someone sort of confronted with this problem, they are classic matters of human judgment.
Exactly, yeah. And no amount of conjecturing whether or not the aircraft went north, east, west and turned west, east, north, is going to help you with figuring out what it was that was really going on in the mind of the person who may or may not have been conscious in the cockpit.
So I find this story fascinating, and I find it fascinating just as an example or a case study, looking at our movement towards autonomous machines, whether it's self-driving cars, whether it's machines that aid with healthcare work. One of the things this seems to highlight is that the machines were very good and very useful. And as you said, they sped up the process of calculating. But at the core was that initial set of assumptions about pilot's intentions and what was going on with the pilot. Everything else flowed from that initial set of assumptions.
Exactly.
So I'm wondering if there's something just from your experience with this that you think it tells us about the way things like self-driving cars would need to be designed, or the thinking that would need to go into designing self-driving cars.
So I think there's a distinction between aspects that you could hope to measure. So you could imagine that a computer could look at video from a dashboard camera, could look into the eyes of the human being and try to make a judgment as to whether they were concentrating or not. You could kind of imagine that, and it probably wouldn't work very well, and you could imagine that people could do lots of research to make it better, and you could kind of see that happening. But I think that there will always be these sort of scenarios that are outside the domain of experience, really, of the computer. And when that scenario crops up, or such a scenario crops up, I think there's a need for a human to impart the knowledge that humans have and the ability to make judgments when we don't have knowledge. I think that's probably also something that human beings can do because we're conscious, whereas a computer that, at least today, is not conscious can't achieve.
Simon Maskell, thank you so much.
Thank you. It's a pleasure.
Simon Maskell is a professor of autonomous systems at the University of Liverpool. Next episode, we will speak with Louise Dennis, who is a researcher in the Autonomy and Verification Laboratory at the University of Liverpool. We will discuss the ways many of the judgment calls Simon describes are in fact ethical choices. If you haven't already, please subscribe to the podcast on iTunes or wherever you get your podcast. And if you have a moment, please give us a rating or write a review, or even better, share this podcast with a friend. It really helps. And if this episode has piqued your interest in big data, you should check out the University of Liverpool online. You'll find some brand new programs in big data analytics and information systems management. We're going to put the link to the website in the show description. Thanks so much. We'll talk to you next time.
You're listening to the University of Liverpool podcast, brought to you by the University of Liverpool online programs. Make a plan to advance your career today. Study a postgraduate degree with a world-class university without leaving your home or full-time job. You don't have to go far to go further.